Mesopotamia, often considered the cradle of civilization, was home to ancient cultures that made extensive use of clay for various purposes. The Sumerian, Babylonian, and Assyrian clays played a crucial role in the development of societies. Take this one. On this tablet is some of the earliest writing from anywhere in the world. The text records beer given to workers as part of their daily rations. It was made around 3000 BC in what is known today as southern Iraq. These guys are good taste. Studying clay reveals a lot about past civilizations, but a recent cross-interdisciplinary study aiming to basically combine archaeology with physics through chemistry has shown that these clays might actually be telling us something important about Earth's magnetic field's evolution. But first, please hit the like button and write more in the comments, as YouTube is not a fan of these kind of videos. Now, let's get started. First things first, what is clay? It is just a type of naturally occurring sedimentary rock or soil, primarily composed of fine-grained minerals, aluminum silicates, and variable amounts of water. Its unique plasticity makes it easy to be molded and shaped when wet. This is what ancient civilizations found very convenient, as clays could effortlessly be employed to make pottery or bricks. Mesopotamia, located between the Tigris and Euphrates rivers, had abundant sources of clay. The deposits were easily accessible and widely distributed. No wonder they made such extensive use of them, whether it was to create vessels, containers, or decorative items. The concept of writing in Mesopotamia differed significantly from its contemporary form. Initially, it manifested as basic counting marks, often accompanied by a non-arbitrary symbol represented through simple images. These were impressed onto clay tokens or, less commonly, carved into wood, stone, or pottery. This practice emerged as a means to accurately record the quantity of goods involved in transactions. Its inception coincided with the advent of agriculture and the establishment of permanent communities centered around increasingly large and organized trading marketplaces. These marketplaces were designed for the exchange of commodities such as sheep, grain, and bread loaves. Transactions were meticulously documented using clay tokens. These tokens, initially petite in size, persisted from the prehistoric Mesopotamian era around 9000 BCE to the onset of the historic period circa 3000 BCE, when the widespread adoption of writing for recording purposes commenced. If we know anything about these past civilizations, we have to thank clay tablets for it. However, a recent study suggests not only can we understand these past civilizations better, but even get a sense of what the Earth's environment was like back then. This would in turn allow us to reconstruct the evolution of key physical aspects that have always shaped life on Earth, for instance, the magnetic field. To better understand how it's possible for a clay tablet to contain information about the magnetic field of Earth, we have to turn to the atomic world for a second. Upon closer inspection, one discovers the presence of iron in clay. As widely understood, iron possesses magnetic properties, with its molecules aligning themselves based on the magnetic poles. This alignment occurs selectively, triggered by specific circumstances. For instance, during the drying or firing of clay, iron molecules within it can align with the surrounding magnetic field. Significantly, the art of pottery making inadvertently sets the stage for this alignment, creating optimal conditions for information storage. In essence, every Mesopotamian artisan engaged in pottery was not merely crafting art or practical tools. Without them knowing, they were also archiving valuable information, perpetually freezing it within tablets that detailed, for instance, the rightful portions of beer allotted to the workers. An intriguing aspect is that the alignment of iron in clay is influenced by two factors: the direction and the strength of the Earth's magnetic field at the time of clay formation. While the first factor may seem straightforward, after all, magnets naturally align with their north or south poles, and opposites attract, the second factor adds a layer of fascination. The strength of the Earth's magnetic field at the specific moment of clay formation becomes a key element. As a result, clay tablets possess the remarkable ability not only to inform us about the movement of magnetic field poles, but also to provide insights into the historical strength of the Earth's magnetic field. This dual capability makes them valuable archives of information about the direction dynamics and the intensity fluctuations of the Earth's magnetic field over time. The phenomenon described so far falls within the realms of paleomagnetism. a discipline that studies the preserved magnetization in rocks or sediments. In the context of archaeology, this field of study extends to archaeomagnetism, where the magnetic properties of archaeological materials, including fired clay artifacts, are examined. By analyzing the magnetic signatures within pottery, researchers can get information about the Earth's magnetic field during the firing event, providing insights into both geological and archaeological timelines. Now, take a moment to realize the importance of what we just said. Say we have a clay tablet, and somehow we know it was made by Mesopotamian people, sometime between the 12th and 9th century BCE. If we manage to study the clay and inspect it to extract information about the magnetic field, we would then have cracked the code to understand the evolution of the magnetosphere's strength over the course of centuries. On the other hand, there's also the possibility that our magnetic field has not undergone any change, and it has been constant since Mesopotamian times. However, the Californian team that conducted the study, called Geometric Intensity Spike Recorded in High-Resolution Slag Deposit in southern Jordan, found out that, indeed, the magnetic field has changed, and it has changed quite a lot. 17 clay samples spanning 200 years yielded archaeointensity results that demonstrated very rapid changes in field intensity in a period of overall high field values. One remarkable finding involved the identification of a magnetic field intensity ranging from 80 to 90 microtesla, a notable increase compared to the current field strength of approximately 50 to 60 microtesla. Now, you might be wondering how they determined this strength. In a straightforward approach, they reproduced pottery and subjected it to controlled ovens with varying magnetic field strengths. Subsequently, they compared the magnetic records in the clay to those within the recreated pottery. By conducting this method, the research team successfully generated a plot that illustrates the magnetic field variations, revealing the distinct characteristics of the ancient magnetic field intensity. The magnetic field evolution plot visually illustrates the changes in the magnetic field over time. Approximately 2,000 years ago, the magnetic field registered at a level of around 60 microtesla. An intriguing shift occurred roughly 1,000 years ago, marked by 3 to 4 closely spaced spikes in the plot. Subsequently, starting from 500 years ago, a descent in the magnetic field values brought them back to normal levels. The pattern shown in the plot is known as the Levantine Iron Age Geometric Anomaly. Indeed, the Levant region boasts a wealth of well-dated archaeomagnetic artifacts, which are ideal records of the intensity of the Earth's magnetic field. These artifacts take spot readings of the geomagnetic field as they cool, and can therefore provide a high-fidelity record of geomagnetic variations for this region, provided they are accurately dated. Over the past decade, many studies have contributed to a relatively coherent intensity record for this region, resulting in the Levant Archaeomagnetic Compilation. This image showcases geomagnetic field intensity over time. The location of the sediments are indicated with a star. The area for which the highest magnetic field values for the corresponding time is given by the black circle. The distinctive pattern of the Levantine Iron Age Geomagnetic Anomaly suggests a significant event may have transpired, altering the Earth's magnetosphere noticeably. The nature of this event remains a mystery, with no definitive answers. However, scientists dedicated to studying the Earth's interior might possess some hypotheses. In the world of current scientific ideas, it's widely believed that a planet's magnetic field comes to life in its outer core. But picture this: Earth's outer core is a zone of hot liquid metal beneath its surface. The key ingredient here is the flowing molten metal. Imagine it as electric charges on the move. This dynamic action is what whips up a magnetic field, like a protective blanket encircling our planet. We call this shield the magnetosphere. Perhaps something shifted in the outer core, or another event occurred in that region, causing the spikes observed in previous plots. Whatever it was, it consistently amplified Earth's magnetic field. Understanding the reasons behind the strengthening of the magnetosphere is crucial for us humans and our survival. Without a magnetosphere, life on Earth wouldn't exist. Additionally, the magnetic field's interaction with solar wind particles shields the Earth and safeguards satellites in orbit. enabling reliable communications and the use of tools like Google Maps. If the magnetic field were suddenly turned off, living on Earth would pose significant challenges. This is also the reason why magnetic anomalies constitute a potential hazard. Think about the South Atlantic Anomaly, right east of South America. In this specific region, where the Earth's magnetic field weakens, the implications extend to satellite malfunctions. Passing through the anomaly, satellites and spacecraft may encounter disruptions in communication, navigation, and critical functions. Moreover, the weakened magnetic field allows heightened radiation exposure. This increased exposure to charged particles from the Sun poses risks to both manned and unmanned missions, impacting the health of astronauts and the functionality of electric equipment. Beyond space endeavors, magnetic anomalies like the South Atlantic Anomaly can impact air travel. Commercial aircraft passing through such regions may face challenges as the altered magnetic field influences onboard navigation systems, affecting the safety and reliability of flights. These anomalies are often associated with geomagnetic storms, triggered by interactions between the Earth's magnetic field and the solar wind. Geomagnetic storms can induce electric currents in power lines, leading to disruptions in electric grids and potential damage to transformers. Additionally, magnetic anomalies can introduce errors in global position system (GPS) information, crucial for navigation accuracy in various applications such as maritime and aviation. Successfully managing the potential risks associated with magnetic anomalies requires continuous monitoring and understanding of Earth's magnetic field fluctuations. This further emphasizes the significance of studying clay tablets. It's remarkable how a seemingly ordinary material like pottery can aid in unraveling historical events. This underscores the influential role of science, spanning disciplines such as chemistry, biology, medicine, and engineering. Science serves as a unifying force, actively contributing to the improvement of our world. Hey, this is where the video ends. Thanks for watching. What would you guys like to see next? Let us know in the comments below. See you in the next video.